everyone. This is my Physics 2, Lab 2 on charge tape revisited. And so the purpose of this lab today is to revisit the concepts from Lab 1, but instead of modeling the tapes as singular point charges, we're going to model them as a distributed line charge. And so what that basically means is, we're still going to have the principles of F equals ma, Newton's second law, equilibrium, the force of gravitation, but instead of modeling the tapes as singular point charges, we are going to divide the tapes into a bunch of tiny little charges, which will then kind of measure, or then kind of add them all up collectively, and see what the net interaction between all these small charges is, to then get our final tape charge, which is this number right here. So that kind of contains the superposition principle of adding up a lot of different charges together to get the net charge, as well as the charge density and divvying up the tape. But now moving forward here onto our lab details and visual, here, just like last week, we have a ripping of 2 tapes off of a central tape, and then from there that's going to positively charge each one, and then we're going to hold the bottom tape up to the top tape until the top tape floats but remains still, and thus is in equilibrium with the gravitational force, and we're trying to find what that charge is on both of the tapes there to kind of cause that interaction, right? So here are kind of some of our starting metrics here. Moving forward here, we kind of define that in the glow script model here, as well as defining our functions that we're going to use today. So we're obviously going to use Coulomb's law to calculate each of the individual E fields between the charges, which is right here. And then we're also going to get the line charge function, which is going to divvy up our different tapes into n number of sections. And so moving here now to actually using the line charge function, we're divvying up the tape into 100 pieces, or 100 individual charges lined up together, all positive charged. And then from there, we are going to make a for loop, which kind of loops between both the top tape and the bottom tape charges, and calculates the net electric force from each of the interactions between the small little charges on each of the tape, with the 100 charges on each of the tapes, right? Which kind of adds them all up together here. And so then moving forward with our calculations to our final calculation, we originally in this slide, or in this model, are using an estimated net charge, but we now need to scale that up to the level of the force mg, or the gravitational force, to then get our final accurate charge number that we're looking for here on the tape, right? So that's kind of what we're doing right here. We're scaling up Q to then kind of account for the force of gravitation, and that'll give us our final charge per tape, which is seen right here in our model, right? And so you can see the visual. We have the gravitational force pointing downwards with the yellow arrow. We have the white arrow representing the electric force. And we have all these small little individual arrows here representing the small little point charges, or small little charges on the top piece of tape. Then moving here to our old Lab 1 model, how it kind of differs, we can kind of just see there's just 2 forces acting, just one top, one bottom, and these kind of represent the different point charges that we use in just Coulomb's law. But now moving forward here to our lab assumptions that we had, we kind of assumed again that the charge is uniform across the entire length of the tape, but certain places could have a higher charge. And so kind of alongside that, we also assumed that only electrostatic forces are present in the system, with no air resistance, no friction, nothing like that, right? And number 3 is kind of tying into that. There's no horizontal components of force in our lab either. And then fourthly, the tapes are modeled as perfectly straight, but when we did our experiment, in actuality, there was probably a slight bend to each of these tapes, which affects their separation distance. And so finally, for our what if, what does it mean questions, basically asking us, what if we modeled it as a single point charge like in Lab 1? And so here we can clearly see that our Lab 2 charge that we calculated is greater than our Lab 1 charge. And so if we modeled as a single point charge, we would have a smaller estimated charge on the tape. And so moving forward here, why do these estimates differ? Well, that's because that in Lab 1, we assume that R is the smallest it can be, right in the middle. So if we put the point charge right in the middle of the tapes and we separate the tapes by a certain distance, that is the closest possible distance between the two pieces of tape, and thus there's less Q as well. So lesser R means lesser Q according to the Coulomb's law equation, right? And so in lab 2, we spread out all of the charges, so there's a greater overall R, and what that means is then a greater overall Q to counteract that, to give us our charge. And it's very likely that lab 2 is closer to the real value due to real objects being extended bodies and not singular points like lab 1's charge.